One of the reasons we study color is in order to be able to manage it well. With the advent of computers into the design process, the onus of responsibility for managing color shifted from production houses, commercial printers, and production artists onto designers themselves. So the designer needs to understand the basics of what's going on, why color doesn't quite sync between devices, and how to bring it as close to syncing as possible. So the problem is essentially illustrated here as we have printers and computers, and everything has its own way of reproducing or producing color. And so you have all these different ideas about what color is, and if you are working on the computer, you want to print out on the printer, it doesn't link up. There's a variety of reasons why that happens. So there was a solution back in the 90s where there was an interpreter where everything spoke to the interpreter and the interpreter translated and sent the information back out to the various devices. So we have a standardized definition of color in the digital realm. Before we go further, let's just clarify some of those peripheral definitions that you would need to know. A gamut is a complete range of capability or scope either of reproducing or producing color. So a scanner would not produce color, it would reproduce it. Whereas a computer will produce color, a printer will reproduce it. So every device, camera, scanner, printer, mobile phone, has a range of capability or scope in terms of color. A gamma is not to be confused with a gamut. A gamma is related to luminance. If you remember the properties of additive color, luminance is the amount of light. So gamma is the range of luminance capability within a device. Color space is a volume. We talked about color spheres back when we were talking about the Hue circle. The Hue circle is a flat geometric understanding of color relationships, but color actually exists in a three-dimensional understanding. So the Hue circle, being two-dimensional, is an abbreviated form of that volumetric understanding. Color spaces actually exist in volumes. And in Photoshop, those color spaces are known as models or modes. Color management is the process of controlling color between devices. So when color is converted from, say, the additive system on your computer to the subtractive system on your printer, color management has to be invoked in order to bring the two into alignment as much as possible, and so that colors match from one space to another. And the idea of color matching is basically that we get the colors to look alike in the different color spaces. Calibration is the idea of adjusting a device, a computer or a printer, so that color can be matched. A color profile is a set of definitions of color. And when you calibrate, when you color match, your various matching software, your interpreters, are going to look at the definitions of color and try to pull them together and map them so that they align. A working space is a simulated space of color so that what you're seeing on screen is going to appear as it will be printed out. Even though you're working in RGB, you can see what it will look like in CMYK. When something's out of gamut, it means that things are falling outside an acceptable range of color capability. Conversion is basically changing from one color space to another. And the way that conversion happens is through a rendering intent. And we'll talk about those in a minute, but how are colors going to be matched? Are we going to use this method? Are we going to use that method? White point is the highest luminance on your computer monitor. So it's basically how white is the whitest white that your computer is capable of creating. Remember back to additive and subtractive color, our first couple of weeks in the course. In subtractive color, we have the hue circle and we have the additive hue circle, but we talked about color actually being volumetric. The color circle is a two-dimensional representation of a three-dimensional reality. Kind of like a drawing of a person. It's a two-dimensional representation of a three-dimensional reality. All color exists in some sort of volumetric space. So here's a two-dimensional representation of three-dimensional realities. If we look at the total perimeter, we can say that this would be visible light. That's the color capability within the range of visible light from red on one end to violet on the other. Color film, traditional color film like Ektachrome or Kodachrome, which by the way is not being produced or developed anymore, is much smaller, and it's represented by the white perimeter. Your color display is represented by the gray triangular perimeter, so it's smaller than color film. Printing is an even smaller gamut. So if we have coated paper, bright white coated paper, you have a larger color capability than if you're printing on newsprint, which is represented by the dotted line. Here's a simulation. If this is the range of RGB color, the conversion to CMY, going from the additive to the subtractive, you can see the dullness of CMYK color comparatively to RGB. So this is what you're dealing with. If this is your display, this is your printer. These are different color modes, spaces, volumes, or modules, however you want to term that. Grayscale color space is a single component. It is a subtractive color space, meaning that you have black and white and all your range of grays, usually about 24 levels of gray between black and white, and it's basically a single component. It's white or it's black. With RGB, you now have three components. You have the amount of red, the amount of green, and the amount of blue. It is an additive color space. HLS is hue, luminance, and saturation. You should recognize those three as the additive properties: hue, luminance, and saturation. Three components, so volumetric, height, width, and depth. It is also additive. CMYK, if we take away the K, which is an add-on, we have CMY. That is three components. It's a tristimulus. It is subtractive, and colors are defined by the amount of cyan, the amount of magenta, and the amount of yellow. Hue, saturation, and brightness is also subtractive. Some printers will use a CMYK, some printers will use an HSB. And HSB is trying to emulate the HLS. It's the same idea, brightness being kind of a misnomer for luminance. It's brightness in this case does not mean saturation, it means luminance. It is a subtractive understanding. CIE stands for the International Commission on Lighting, and it's also known as lab color. It is an additive color space. Spectral color is measuring the wavelength, so you'd have a spectrochronometer which you actually place against the color, and it measures the wavelength frequency that is being reflected. Spectral in itself is additive because you're measuring wavelengths, so you're measuring light, but you can measure either your monitor or you can measure reflective art, a reflective surface like a magazine page. This illustration shows a comparison of various color spaces, so you can see the idea of volume. Color is either cube, or it's like a cheese wheel, it is a disc, or in this case it's that cone idea. And then we also have a sphere, so depending upon the color mode or the color space, it's going to have a different form. Grayscale is a single component color space. It's basically luminance. Translated subtractively, it's value. Higher value, lower luminance, higher luminance, lower value. So we go back to that additive understanding of the luminance property. How much light do you have? and then the subtractive idea of value, which is the lightness or darkness of a particular color. CMYK can be configured within a cube having height, width, and depth. And you have a yellow component, you have a cyan component, and you have a magenta component. And colors exist anywhere within that space. As you can see, all the little dots represented here are positions within that color space. Each position is a different color. RGB is the same idea. You will have red, green, and blue, and there will also be magenta, cyan, and yellow. And they correspond to each other so that magenta sits across from green, yellow sits across from blue, and cyan sits across from red. It's complement in the additive. Spectral, of course, is wavelength measurement, going from red to violet. And that is where you actually place the device against something to measure its luminance and the wavelength frequencies that are being reflected from the surface. HLS, an additive color space, deals with the amount of luminosity versus lack of it, the hue, and then the saturation moving from the center outward. So in a way it has a related understanding to the volume of color in the color sphere. So we have lightness and darkness as polar opposites. We have hue running around the circumference, the perimeter, and then saturation going from the outside, being highly saturated, to the interior core, which has no saturation. Lab color is the International Commission on Luminance, or lighting. It deals with polarities between green and red, yellow and blue, and everything in between. It exists in a sphere. And lab color is denoted with plus or minus. It has a algebraic understanding. The International Commission on Illumination, and it was the first attempt at standardizing color. It actually came about because of manufacturing and the issues of trying to match color in manufacturing and interior and architecture. The ICC, the International Color Consortium, was founded in 1993, and it was founded because every device had a different color space, and there was no way to bring everything together to create or to speak a common language until the ICC came along and said, okay, this is the language that you get to speak. So if you're working in Quark, you're using ICC profile. If you use a Dell computer or a Macintosh, an Apple computer, you've got an Android phone, you've got an iPhone, you've got a BlackBerry, you're using ICC color profiles. So the ICC came together and said, okay, this is how color will be defined cross-platform and cross-software. So now everything, instead of having its own color definitions, has a common language to speak. And so this is the device-independent idea. In printing from my display to my Epson printer, in the print dialog box, I can go in and look under advanced, and there's rendering intent. And basically the rendering intent is going to tell the software, the CMM, the color matching module, how to interpret the color. Rendering intent is how the colors are brought together between the additive and the subtractive. It is basically, how do you get this much color, all that color information, comfortably inside a smaller space? Do you squeeze it all in? Do you eliminate some colors? Do you keep some out and only take certain ones? You go from a larger space to a smaller space. So the first rendering intent is probably the most often used. It works well with continuous tone images like photographs and illustrations. It will scale all the colors in the larger gamut to fit into the smaller color space, which means that every color in the larger space gets altered. It retains value contrast, which is really important. If you lose value contrast, you lose the depth in the image. It gives you an eyeballed result where colors are similar but not exact, of course, because everything has changed. A saturation match will maintain relative saturation levels of both gamuts, the larger one and the smaller one. And it will do this by converting things that are out of gamut, meaning they won't fit into the smaller space, to colors that are already in the space that have the same saturation. Instead of squeezes or scales, it'll actually convert. It'll say, well, this is close to that, so we're going to convert this to that. Saturation will maintain the intensity. It will reduce the value contrast. The depth of image and the range of color, the range of chroma in the image will be compromised. And this is best when you're dealing with information graphics. Spot color. And then there's colorimetric. There's two options for colorimetric. One is where the white point does not change, and one where it does change. In colorimetric, the overlapping colors that are in both gamuts, the larger and the smaller, remain unchanged. And anything that's out of gamut, in other words, anything in the larger space that won't fit into the smaller space, gets remapped or changed to its nearest neighbor in the smaller space. You have a reduced amount of chroma range. Your white point changes, and colorimetric is best used for spot color. With absolute colorimetric, the white point itself does not get remapped when it moves into the smaller space. And it simulates the behavior of another device. It is best for proofing. When you go to print on your desktop, you will get an option of color management in your print dialog box if you go to the advanced settings. And within the settings, you have a choice of the printer managing the color or the actual software that you're printing out of managing the color. Since the printer is the subtractive destination space, it makes more sense to have the printer manage the color. So you will look at color management, and then you will look at, is this just a basic document? What kind of thing are we printing? Is this going to be a proof? Is it going to be just an in-office document? And I always go to the print manages the color. And then you see here the paper type. If you remember back to our discussion in the first lecture about surfaces, surface quality affects how color is perceived. So glossy paper will reflect color differently than uncoated paper. And so the printer profile is always going to ask you, what kind of paper are you intending to print on? And then of course here's your rendering intent, and this is set for relative colorimetric. And black point compensation, that's a gamma issue. You have your white point, and so the black point is the darkest. It's the opposite of that. So here's all the paper options within the Epson printer that I work with. When you're designing websites, you can specify RGB, but most often what's used is hexadecimal. Remember that color displays and the internet are always going to be using additive color. So when you are dealing with websites, you can use a standard English name like red, green, blue, or you can use RGB, which would be in this case 255, 255, 255 to get white. So here is the color notation. This is how it's written out to specify red. So you are full on red, you have no green, and you have no blue light coming through the pixel. With hexadecimal, it uses a series of bytes. So you have 3 bytes in a row, and there's a red value, a green value, and a blue value. And within each byte there are 2 digits, and they're either 0 or 1, they're on or off. So you have 6 digits, which gives you the hex or the hexadecimal. And every time you use a hex notation, you need to put the hashtag in front of it. So A full set of zeros is going to give you black. 2 Fs will give you red. If you have 6 Fs, you got white. And generally speaking, it's kind of like almost designating a spot color. If you want a particular color, you can go to any sort of web hexadecimal lookup table. And in this case, this chart gives you the actual English name, or in the code you can specify the RGB notation, or you can specify the hex. This is just to alert you to the fact that there are subtle variations between browsers. In other words, Safari, which is the standard Apple browser, will display color a little bit differently than Internet Explorer, than Chrome, than Firefox. So you see the various web browsers. There's a Safari, there's a Firefox, and there's a Chrome. And the color variations from these screenshots are very subtle, but they are different. When you're building websites, not only do you want to check that your code works well in all browsers, but you want to make sure what your color is looking like in all browsers, because if you go from Safari to Firefox, there's going to be a different color being perceived. So you can see here the school bus yellow is slightly redder than these two. And again, the variations are subtle, but they are there. And again, just like with color proofing, you want to look at the neutral colors, because that's where the variations are going to show up most. So just be aware, browser to browser, color renders differently.